tired, so am I. So I try to be a bit soft today. Those who know already a bit of learning theory, you will understand after, I would say, 20 minutes. And but I will not be often difficult for it. And those who don't know anything, I guess today you will follow, and maybe later on you will follow it. Okay, just I will try to have half the audience awake anyway. So here is the roadmap of this series of lectures. So as the title indicates, I will tell you about statistical learning theory, which is one of the many aspects of learning theory, and maybe the one that has been most developed in the latest years. And it will be a very narrow view of this learning theory, and even on this statistical learning theory. But I try to convey some general ideas, and if you can get out of the summer school with the two ideas that I will introduce in the first two lectures, that would be already good. And so in the first lecture, that will be mostly high-level overview of what it means to study learning theory and to formalize these concepts. So it will be very overviewish, lot of hand waving, and then lecture 2, some basic knowledge. So that will be in the second hour. Okay, there will be a little bit of mathematics here, and then it will become a bit more formal in the remaining lectures. So tomorrow we'll see the PC theory, which is an important thing to know, at least for your culture. And then it will go to more advanced topics. And that will be the first part where we will focus on binary classification. And then, in the latest part, that will be on Saturday, when everybody will be completely exhausted. So I have not much hope to go through all of them, but it's quite an interesting topic anyway. And it will be on real value classification. So when you want to do classification, but with actual real value function. And that has lots of nice properties, and maybe if we go till the end, I will show how to apply all these results to SDN in particular. Okay, so in these first lectures, feel free to interrupt me anytime if there is something you don't understand, because I really want you to grasp the very basic idea at least. So if there is anything that sounds strange to you, don't hesitate. Okay, so lecture 1, we will introduce what is the learning problem. So we'll start by talking about the context. So that will be again the same kind of slides that you have seen in all the previous lectures. Then I'll try to formalize it a little bit, and again tell you about this approximation estimation trade-off. So you will see almost the same slides again, and then finally get to what are the bounds and what kind of bounds we're interested in. Okay, so let's start from very high level, like 10,000 feet above the problem. So what is the learning problem? So we can call it the inductive inference problem. So very roughly speaking, we observe a phenomenon, whatever it is, let's say the weather. We try to construct a model of that phenomenon. So in this last week, it's easy. It's sunny every day, very hot. And then we try to make predictions. So maybe next week it will be again sunny and very hot. Okay, so that's kind of the process. And well, you can think of this as what people do in natural science. They observe the natural phenomena and they try to build a model, which means some kind of formalism that explains what they observe. But in addition to that, in addition to being able to explain what you observe, you want to be able to predict something that you haven't observed yet. Okay? And the goal of machine learning is to make this automatic. So to make sure that computers can do these things by themselves. And learning theory, the goal of learning theory is to understand this process and to formalize it. Okay. So in this series of lectures, I will restrict myself to a very, very limited sub-problem of this inference process. namely what is called supervised learning. So that you have seen lots of supervised learning techniques in the previous lectures, and especially for pattern recognition, which means the classification phase. So that's very restrictive, but at least we can show in this restrictive framework the basic ideas and the basis for constructing wider theories. So what it means, we have some data which consists of pairs, instance and label. So for example, the pair, day and weather on that day, sunny or not, for example. And the label is restricted to be binary, or here +1 or -1. So we have just two possible labels. And we have an algorithm that constructs a function that maps instances to labels. So it predicts, you give it the date, and it has to predict the weather on that day. And of course the goal is to predict correctly, which means to make few mistakes on future unseen instances. We don't care about predicting what weather you have in the past because you have observed it already. Okay, so this is more or less the picture that is in everybody's talk, except that here I'm doing it in the context of classification, and you probably have seen it in the context of regression. So again, you observe some data. Here we have these crosses, these blue crosses and these green circles that are in some space. So these correspond to features of these instances. And we want to find a separation, which means a function that can tell us whether we are on the blue side or on the green side. Of course, this function can be, you can think of any function basically, but you want to at least be able to explain more or less good the data that you observe. So if you want to explain perfectly the data, you would take a function like this, for example, because you want this function to be consistent with the distribution that you observe. Okay, but then you may say, well, it looks a bit complicated, this function. That's very unlikely that the phenomenon I'm observing is so complicated. Maybe the weather is not so complicated. Maybe there is an easier explanation of this weather, and maybe the fact that this green point is here is just an error in my measurement. Maybe I did not measure precisely enough the temperature, or maybe I had sunglasses and I thought it was sunny, but it was there was some clouds and I could not see them. I don't know. So in that case, what you do is say, okay, let's try to find a function that more or less explains the data, but we allow it to make some mistakes on the data, right? So you take maybe this pink function here. Or you can say, well, I really think the process I'm observing, or the phenomenon I'm observing, is extremely simple, and it's linear, let's say, in these features. So I will try to find a linear function that more or less fits this data. Okay, and of course the question is, which one of those three is more reasonable? And that's what we will try to answer in this series of lectures. And let's say the general idea is that there is a trade-off to find between fitting the data, explaining the observed data, and complexity of the function that you use to fit the data. And we'll make this a bit more precise later on. Okay, so again, I think you heard this name several times. So again, general ideas. The idea is to look for what are called regularities in the observed phenomenon. So if you see that every day it's sunny, then it's a regularity. And what it means is that it's something that is simple enough to explain a large set of data. So saying that sun occurs every day is a short sentence for saying today it's sunny, tomorrow it's sunny, the day after tomorrow it's sunny, and so on. So it's kind of the idea of compression and NTL or all these approaches. And once you found these regularities, the nice thing is that they may allow you to generalize. Because if you compress or if you extract some relevant information, some pattern from your data, then it's likely that this pattern will hold in the future. So the guideline is to choose the simplest model that is consistent with your data, or consistent up to a certain level if you allow some error. And it immediately raises the question of how to measure this complexity or simplicity. And there are many ways of doing it. In physics, people try to find laws that explain, I don't know, the movement of planets with a limited number of parameters, and the less parameters you have, the simplest the law, somehow, in the view of physics. Or you can use decryption lengths. So if you can describe these regularities with a short sentence, somehow you can say that it's simple. Or you can use other notion of number of parameters and so on. And we'll try to see that there are more or less clear ways of explaining or of expressing this simplicity within this theory that I will present. Okay, so that's again general ID and very widely known ID, but I will give it a little twist here. So what does it mean that we have no free lunch? It means that if we don't make any assumption, or if we don't restrict in any sense what we want to do, then there is no way we do it somehow. So if we don't make any assumption about how the past is related to the future, there is no hope, right? If you say the weather is a completely random phenomenon, then there is no hope that we can predict it the next day. Okay? Prediction is impossible. Now, even more, even if you have some assumption that the past is related to the future, then if you don't make any restriction on the possible phenomena that you will have to cope with, then you cannot really generalize. Because the function that maps the weather of the next day from the weather of the previous day can be arbitrarily complex. And if this is the case, then there is no way that you can find these regularities. I mean, if regularities can be arbitrarily complex, then there is no hope. So we need to make some assumptions. And, well, okay, this, when I say simplicity is not absolute, it means that in abstracto there is no way to define what is simple, because it boils down to choosing a certain language to express these regularities. And if you change the language, then the regularities that you obtain are different. So there is no universal way, let's say, of quantifying what is simple. Another kind of general idea is that data will never replace knowledge. What does it mean? It means that even if you observe long enough the weather, it doesn't mean that you will be able to express, to predict the weather in the next day. Because somehow you need these assumptions. You need to know something about the weather. And, okay, even if you don't know, you need to have some intuition about it. Let's say maybe it's, the phenomenon is linear or is quadratic in certain parameters. And this is the fundamental equation. So whenever you want to generalize, of course you need to start with data, but you need to have some knowledge. And this knowledge can be what is simple and the choice that you make. Okay. All right. Enough of hand waving. Now we slowly get into more precise things. Okay. So, as I said, we need to make some assumptions about how future observations are related to past ones. So we need to assume at least, say, the law of physics do not change from one day to the other. Otherwise, there is no hope, right? So we assume some kind of stationarity of the phenomenon, of the laws of nature. And also we need to constrain this phenomenon, and that's where the notion of simplicity and certainty needs, in addition to this assumption that the laws of nature hold every day, we need to assume that they are simple also. Or simple enough for us to grasp them from a finite number of observations. So what is the goal now of this learning theory is to answer these questions. So how can we make predictions from the past? How is this possible at all? And how can we show it in a mathematical way? And what are the assumptions that we need? And this goes through three levels, let's say. So we first have to define formally what is learning and introduce some notation, some mathematical quantities and objects, define what is this word generalization and what does it mean to overfit. That's something that these are words that we hear in many lectures, but I will try to make them a bit more precise. And then, given these definitions, then we will be able to characterize the performance of certain learning algorithms and give quantitative results. And then hopefully, from this characterization, once we understand how learning algorithm works and when do they work well, when do they work bad, then we may be able to design better algorithms. But I will not really detail this in this set of lectures. Okay, so there is still no equation there. Okay. We're getting close to it. Oh, maybe I can stop. Okay, is it clear? Maybe I can come back to the bit. No? Okay, well, that's very easy anyway. So, what is the model that we will assume for how the data is generated? Okay, so we say laws of nature are constant, and these we will model in this way. We will have a probabilistic model, and probabilistic models are nice because they allow us to account for uncertainties and for mistakes. And we will assume that the data comes to us, so the weather, like every day, comes in this way. We have independent observations who somehow, well, it's not the case in the weather, but we will make this assumption anyway, that we get some data that is independent from each other. So the next data that will come does not depend on the previous data that we have observed, but they come from the same distribution, and that's where the stationarity comes in. So we assume that there is a single distribution or process or phenomenon that generates this data. And why do we make these two assumptions? The assumption about independence is related to the fact that when we have independence, in some way, we can say that each new data that we get gives maximum information about the process we observe. Because if they are dependent, then it means there are certain redundancy in our data. And we can only do worse if we have less information somehow. So why not assuming that they are independent? At least we know what we can do in the best case. And if they are not independent, too bad. An identical distribution that is the stationarity of this underlying phenomenon. Okay? So now we can introduce some notation. So we have instances, and if to these instances are associated labels, as usual. So we denote by x, curly x, the input space, y the output space. So our instances live in this space, and this is just a set of two values, +1 and -1. These are the labels. Okay? And okay, now we make the assumption a bit more formal. We assume that the pairs x and y that we observe, so instance and label associated to this instance that are taken in this set are distributed according to P. Okay? And P is this probability distribution that generates the data. And this is supposed to be unknown. We don't know it. We can only observe a certain sample from that data. So we observe a sequence of n IID pairs. IID means independent and identity distribution. Okay? So this is the data that we observe, which is sampled from this distribution. Okay? And this remains fixed throughout. And our goal is to construct a function that maps these instances to labels, so that predicts the label of each new instance, where the new instance that we will have to observe, or for which we'll have to predict the label, will be also sampled from this distribution P. So now we have to introduce some kind of criterion to determine whether the function G that we construct is good or not, right? So, okay, so this criterion is what is called the risk. And the risk is actually the probability under this phenomenon that generates data xy of the prediction g of x being wrong, being different from the label that should have this instance x. Okay? So you see here that we don't want to be accurate all the time. We just want to be accurate on this data that is generated by our distribution P. So we don't care about being about predicting the correct label for all values in our set x. Remember this this input space x. Maybe the phenomenon is such that certain instances will never be observed. In that case, we don't care about predicting them well. Okay? So we really want to be good in probability, which means only on those instances that are likely to occur often. Okay, so that's the definition. We call the risk R of g, of the function g, the probability of mistake, and we can also write it in this way, the expectation, so this means expectation under this distribution P of this function here, which is the indicator function of g of x different from y. So this is a function that is equal to 1 when this is true, and equal to 0 otherwise. And if we take the expectation of that 0, 1 function, then we exactly get this probability. Okay, that's probably very clear for everybody who has done probability before, but it may not be easy for other people. So is that okay? Okay. So we will play several times with this kind of property that we can express the probability of a certain event by the expected value of the indicator of that event. Okay, but of course we don't know P. That's the problem. So we cannot really compute this quantity. We cannot measure it. So how can we say whether a function is good or not? The only thing that is available to us is the data, and the data is sampled from it. And so what we can do instead of computing this risk, we can compute what is called the empirical risk, which means the agreement of our function g with the data that we observe. And that's what is called the empirical risk, Rn of g. So whenever I put the an index n, I refer to a quantity that depends on the data. Okay? And n is the size of my sample. So I have instances x1 to xn, y1 to yn. And this is what is called the empirical expectation of this indicator function here. And what it measures is the fraction of errors that I make on my data, because I rescale it by the number of instances I have. So you see there is some kind of very nice similarity between these two quantities. Here I have an expectation of a function that can take value 0 or 1. And here I have also an average. So it's also an expectation, but under a different probability measure, which usually is called the empirical measure. It's a probability that corresponds to putting mass 1 over n at each data point. So are these notations clear for everybody? Now, okay, I introduce a bit more notation, and hopefully I won't you won't drown in this notation. So again, this probability measure P. So it's a probability measure on what is called a product space, which means it's probability over pairs x and y sampled from 30x, 30y. And we can always decompose it as marginal distribution. So this is only the distribution of the instances. We don't care about the labels. And the probability of the labels given the instance. So the conditional probability of the instance given the labels given the instance. And when we do that, we can introduce a number of functions that depend only on the instance and that are related to what is the label for this instance. And the model we have is that we may not have one fixed label for each instance. So a given instance, a given x in our space, can have many different labels. I mean, can have one of those two labels, +1 or -1, and that can be random, which means that there may be errors in the measurements. That's exactly what we want to model. We want to model possible errors. Okay, so if now we look at a certain instance x, and we condition on that event, so somehow we fix our observation, and we look at the labels that can occur for this instance x, and we take the expected value of the labels. So these can be +1 or -1 with certain probability. So the expected value can be written in this way. It's also twice the probability that y equals 1 minus 1. That's easy to see. I mean, essentially, you have the expected value is the probability that it's 1 plus the probability that is -1 times -1. So probability that y equals 1 minus probability that y equals -1. And that's equivalent to this here. That is usually called the regression function. Okay, so it's a function that, I draw it. So let's say you have your instance space here, 30x, and this is y. So if you take points in this space, like if you look at, say, this x here, the label can be either +1 or -1. If you repeat the experiment of sampling points that correspond to this instance, you will have something like this. And this function measures how often it will be 1 or how often it will be -1. When the function is equal to 0, then it means that you have probability 1/2 of being here or 1/2 of being here. So you don't really know which is the right instance. But as soon as this function is positive at this point, then it means you're more often hitting +1 than -1. And if it's exactly equal to +1, then it means you always have labeled +1 when you are at this instance. And if it's always -1, same thing. You have a deterministic label. Okay, so now we introduce this function t of x, which is the sign of this regression function, and that's we call the target function. And again, on this picture, it tells you, I mean, if eta is here, let's say, then t will be here because you're positive, okay, so the sign is +1, and it tells you what is the label that is most likely to occur at this point. Somehow that's what we are trying to do. I mean, that's what we are trying to find. Because what we really care is to find, for this specific instance, what is the label that we should predict. Remember that our function t is a deterministic function, so we have only one guess. So if I tell you I want to predict the value at x, you should tell me, well, it's t, because that's the label that is most likely to occur, and that's how you can make the least number of mistakes. You will do some mistakes if eta is not equal to 1, because all the time that with some probability the label will be -1 and you make mistakes. And in what is called the deterministic case, where the label does not vary, say at a certain instance, then the random variable y, we describe the label, is exactly equal to this variance function. And eta is always +1 or -1. Okay, and this is also expressed in this way. The probability of y being equal to 1 is either 0 or 1. 0 when the label is -1. Okay, and last function that we introduce is what is called the noise level. And this measures the best error that you can make at a certain point. So again, at this point, x, if eta is at this level, then the best thing you can do is predict +1. But if you predict +1, you will make mistakes whenever the label is -1, which is measured by this difference here. The difference between eta and the value 1 tells you how many times you will make mistakes. And all these functions are defined at each point in our instance space. And of course, we are interested in statements that are valid across the instance space when the points x are sampled according to the probability p. So then we will be interested in the values of the expectation of all these functions. Okay. Again, some broad ideas. We need to make some assumptions about p. Remember, we say we need to make assumptions about how complex is the phenomenon that we try to identify. And this translates here, the phenomenon is distribution P, and we need to make assumptions about this phenomenon. And one thing that comes out of P is this function, this target function T, which is really what we are after. So making assumptions about P means making assumptions about T. If we don't assume anything, then the target function can be arbitrarily complex. And if we have just a finite number of data, so let's say T is very complex, and we observe the value of T only at a certain number of observations. So we'll say we get this value, and here it can be 1 or 0. So here. How can we tell from these things what is the behavior in T in between? There is no way. So we have to assume somehow that T will be more or less flat in certain regions, because then that's where we can generalize from observation at one point to the whole interval. So these assumptions can be of various natures. Can be what's called the preference or prior, and it's some kind of a priorized probability distribution on the possible functions T that we will observe. Or it can be also restriction. That's a special case of this, where we say, okay, we assume that T will be of this specific form. Let's say it will be flat, or if we take only the same value in a certain interval, and then the same value in another interval, and there will be only one breakpoint. That's an assumption. And now there are two kind of approaches for treating the lack of knowledge that we have, because even if we know something, if we know that T belongs to a certain class, then we don't know exactly what function T is. And there are two ways of doing it, or of replacing this lack of knowledge by some stronger assumption. The Bayesian approach is to say, well, we don't know what is T exactly, so let's assume that it can be any of the function in the class with equal probability. The learning theory approach is a bit different. We have some kind of worst case analysis. So we don't say assume that it can be any function equally likely, but we say assume that it's the worst function. So somehow there is someone who chooses this function and tries to make us make mistakes. Okay, again this picture. So in view of what we are saying, so T now here in this picture is the function that is 1 on one side of this boundary and -1 on the other side. Okay? And this boundary determines the complexity of the function, the target function T. So the last two notions that we introduced are this notion of underfitting and overfitting. What does it mean to underfit? It means that you have made assumptions that are too strong somehow. So you have assumed that, say, for example, you assume that your phenomenon is linear, so you fit the data with this line here, this red line, but of course it does not really capture the phenomenon, because it's unlikely that the data really follows this distribution, or this, And overfitting on the other hand, is that you're allowing too many possible functions, and you find this complex function here. Well, of course it fits the data, but it fits it too well to be true somehow. Okay. So now I will introduce one very basic algorithm, which is kind of at the heart of this theory. The idea is that you start by choosing a model, so you make these assumptions, and a model means a set of possible functions, so you assume your target will belong to this set, or even you don't assume the target is in this set, but you say, well, I don't care where is the target, but I want to work with an easy enough set of functions. So you can say, I try to fit the data with a linear model, even though I'm not sure that the data has a linear model. But I see what I can do with a linear model. So that's the choice that you make. And now, in this set, then the easiest algorithm is just to minimize what is called the empirical risk, so the fit of the data. So you find the function in that set that looks the best from the data portfolio. And okay, here I have the notion that I have not introduced the base classifier. Essentially, it's the target function. So it's the best classification function that you can hope for. So of course, you may have a problem if this target is not in your model G, but it may not be such a problem. And why is that? It's because you may not be interested in how close you are to the target function, but you may be interested only in how good you do with respect to this model G. And that's what is written here somehow. So the base risk is the risk of the target function. It's the best risk that you can achieve if you allow, if you minimize the risk over all possible functions. Okay? So it's the risk of the target function. Now you can decompose, well, you can introduce the best function in this model G. So you have this set of possible functions. In that model, you can look for the one that minimizes the risk. You call it G star. And you look at the risk of this function, R of G star. And now you compare, so again, Gn, G sub n means the function that you have constructed for the data, from the data. Remember, sub n means I construct from the data. It's data dependent. You look at the risk of this function, that's the risk of the classifier that you have obtained, and you look at how far it is from the best risk, the best possible risk, the risk of the target function. And you can decompose it in this way. The difference between this star. Okay, so that's the best in the class in terms of risk minus the best overall. So what this is, I mean, you cannot hope to do better than this anyway, because you know that you're restricting your class of function to be G. So you know that you will always make at least this mistake, which is what is called the approximation error. It tells you how well your class of function can approximate this target T. And then you have another term, which is what is called the estimation error. That's the difference between the error of the function that you have selected and the error of the best function in your class. And this is really where the data plays a role. Because the data somehow will mislead you. Because you don't have full knowledge of the distribution P. If you had full knowledge of P, you could find G star. If you don't have, then you have just Gn, and Gn might be different from G star. And how much the data is misleading will be captured by this error, this estimation error. And that's the only term in this sum that is random, that depends on the data. And the, one of the most studied objects is really this quantity here. And our goal will be to provide quantitative estimates of this estimation error. Well, of course, restricting ourselves to a single model may be a bit too simple an approach. So we can go a little bit further and say, well, let's not choose just one model, but a series of models. Call it GD. G is some kind of measure of the size of this model, but we'll come back to that later. And in each of these models, we'll pick the best function with respect to the empirical error. So we will minimize the empirical risk in each model. And then, so that's this term that we minimize. Then we compare all the functions that we have obtained, all the classifiers that we have obtained. So say, for example, in the first model we look at linear classifier, the second model quadratic classifier, and so on. And we compare all the best models. And we take the one that has small error, but also has small complexity. And the complexity will be measured by a certain function, certain penalty function of the size of the model. Okay, and this is the term, and we minimize the sum of these two terms. So we try to find a model that is rich enough to fit well the data, but simple enough to have a low penalty. And that's what is called the structural risk minimization approach, or penalized model selection. And this penalty gives preference to models that have small size, and these are the models in which we will be able to show that the estimation error is small. Yes, sorry. The penalty depends on the sample size, but I didn't want to put an n here, otherwise it would have been data dependent. But okay, you can say d, comma, n here. And okay. So another very much related approach is what is called regularization. So if you look at the equations or at the optimization problem, is almost the same. The difference is that we don't assume now that we have a discrete sequence of models. We just choose a very big model G, which somehow contains all these sequence of models, and we choose a function, a functional, so a norm, say for example, or function of G, and which is our penalty term, and we put it here. So now we minimize in this big model the empirical risk plus a term which penalizes the complexity of the function. And there is this lambda parameter, which is called the regularization parameter, and that allows us to trade off fit of the data, complexity of the function. And actually, many algorithms can be solved or represented in this way. You always have, I mean, whenever you want to do some learning, you have to have these two terms in your procedure. You have to have something that measures how well you fit the data and something that measures how complex is your model. And all the approaches basically differ in how they measure the complexity of the function and how they measure the fit of the data. And that's it. Okay, now we get to the last notion I want to introduce in this first lecture, which is the notion of bound. So remember, we have what is a learning algorithm? It takes as an input the data that we present to it, which is sampled from this probability distribution, and it generates a function Gn. And the question is, can we estimate the risk of Gn? Or what can we say of the performance of this algorithm? As I said before, it's a random quantity which depends on the data, and this means we cannot make statements about the risk of Gn that hold all the time, because it may always be the case that we see some data, and on that data we think, oh, Gn is very good, but this data does not capture well the behavior of the whole distribution T. So we need what are called probabilistic bounds. And the bounds that we will be after have this form. We want to bound the risk of Gn in terms of something that we can observe, which is the empirical risk of Gn, and another quantity that will measure these estimation errors. And okay, we can have different types of bounds which relate the risk of Gn to the best in the class, for example, or the risk of Gn to the absolute best, the base classifier. So this, this bound will give us a way to estimate the risk. These bounds, we don't know these quantities, so we cannot use them to really give measure of the risk, but we can use them to have theoretical guarantees on the behavior of our algorithm. Okay. And the last thing I want to mention before the break is that these statements will be probabilistic statements. So what does it mean? It means, let's say we have this database of our nature. So let's say this is the nature. From this nature, we sample data. So we get the sample xi, yi of x1, yn, y1 to xn, yn. But we could repeat the experiments. We could do it again. So the next day, we also sample another sample of data. Same thing, x1, y1, xn, yn. And we can do that many times. And if at each time we construct a classifier Gn, and we ask what is the error of this classifier, of course it will depend, it will vary across time. And the statement that we will make will be that for most of these samplings, so maybe for those three but not for this one, the error of Gn will be bounded in this way. So we will have a statement that tells us most of the time when we repeat these experiments, we will have this, the bound will hold true. But in certain cases it may not hold. So if you take a fixed data set, then maybe it doesn't work. But you have to think really in these terms where you assume that you can repeat the experiment, you can sample many times from the same distribution, and you want to say something not on average, but that will be true most of the time. Okay, thank you. So